Assalamualaikum warahmatullahi wabarakatuh. My name is MOHAMAD HILMAN KAREM, CD107107. Today I want to talk about the radiation of the heat transfer. First thing, we have to understand more about the radiation. We have to know the phenomenon of the radiation. The energy of the radiation transfer is the form of electromagnetic form. The radiation mode of heat transfer is independent of medium. It occurs more effectively in the vacuum. From this picture, we can know the radiation from the heat, from the flame. This one is the picture of the radiation. We can know about the radiation. Then we can feel the heat of the sun. Although the sun is 150 kilometers away from although the Earth is 150 million kilometers away from the Sun. There are no particles involved while reaching the heat from the Sun. This one is the radiation of the Sun. This one is the Earth. We can feel the heat of the radiation from the Sun. For the thermal radiation, all objects at non-zero temperature emits the radiation. The hotter the object, more radiation will be emitted. For the greenhouse effect, this is the greenhouse effect. Most radiation is absorbed by the Earth's surface and warms it. This is the radiation from the sun and atmosphere and Earth's surface. Some of the radiation from this picture, we can know that some of the radiation is reflect and some of the radiation is absorbed from the radiation of the sun. The radiation, no carrier or medium to require. Medium participating, a part of the radiation gets absorbed. For the medium non-participating, the radiation passes undiminished. For the fundamental concept, the radiation is emitted in different wavelength and different direction. There are different between it. The spectral distribution and directional distribution. For spectral distribution, it depends on spectra of the light. For the directional distribution, it depends on the direction of the light. For the radiation properties, when the radiation strikes at the surface, a portion of it is reflected, and the rest of the radiation is enters the surface. Of the portion that enters the surface, some are absorbed by the material, and the remaining radiation is transmitted through the material. The ratio of reflected energy to the incident energy is called reflectivity. The transmissivity is defined as the fraction of the incident energy that is transmitted through the object. Absorptivity is defined as the fraction of the incident energy that is absorbed by the object. The three radiative properties all have values between 0 and 1. Since the reflected speed and absorbed radiation must add up to equal the incident energy. This one, the example of the formula. This one is the values between 0 and 1. Three radiative properties. For the black body radiation, we talk about the black body radiation. A black body is the ideal emitter. Energy emitted by any real surface is less than what is emitted by the black body. For the assumption involved, it is an ideal emitter. At every frequency, it emits as much energy as or more energy than any other at the same temperature. It is diffuse emitter. The energy is radiated isotropically, independent of direction. The monochromatic emissive power, and this is the symbol of the monochromatic emissive power, is defined as the rate per unit area at which surface emit thermal radiation at a particular wavelength. The black body has the highest monochromatic emissive power for any given wavelength. From this picture, we can know the difference between the black body and the real body. From the black body, it produces the radiation in uniform. For the real body, the radiation is in non-uniform condition. Black body is uniform. The black body is said to be a diffuse emitter since it emits radiation energy uniformly in all directions. From Planck criterion for a perfect black body, it allows the radiation to enter but not reflect, possess a minimum thickness adequate to absorb the incident radiation and prevent its re-emission, satisfy severe limitation, weapon scattering to prevent radiation from entering and bouncing back. That is for the Planck criterion. For the Planck's law, this is the law of the Planck's Planck. As you can know, there are C1 and C2. This is the values of C1 and C2. C1 is 3.742 and C2 is 1.439. I think the value of the C1, C2 is fixed. Emissivity. We want to know more about the emissivity. The ratio of emissive power of body E to the emissive power of black body at the same temperature is called the hemispherical emissivity of the surface. This one is the emissivity depends on temperature, wavelength, and the surface smoothness. EB is equal to 1. From the formula, we can know that ACB is equal to 1. In the most solid and liquid, the radiation emitted from the interior are absorbed by the adjacent molecules, thus making it a surface phenomenon. In gases and semi-transparent solid, radiation is a volumetric phenomenon. This is the Wang displacement law. Blackbody radiation curve for a different temperature peaks at the wavelength inversely proportional to the temperature. This is the max power. The values of max power is 2897.8. For the gray body, there are different between the black body and the gray body. A source with low for the gray body, a source with low emissivity, lower than 1, independent of wavelength of light of that is referred to the gray body. Gray body will have emissive and absorptive power less than the black body. Diffuse emitter is a surface for which the intensity of emitted radiation is independent of direction. Diffusive gray body approximation of gray bodies make the otherwise complex study and analysis simple. This is the difference between the black body and the gray body. The gray body is defined as a body whose absorptivity of surface does not vary with variation in temperature and wavelength of the incident radiation. This one from the picture we can know the black body is more higher than the gray body. Alright, that's all for me. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AMIR RAAUF bin Abdul Rashid, CD170043. So today, I will be presenting in the heat transfer of view factor exchange between surface and the radiation network. So firstly, I will be presenting about the view factor. So as you can see, the view factor is a purely geometrical quantity and is independent of the surface properties and temperature. It is also called the shape, configuration, angle factor. So the view factor based on the assumption the surface are diffuse and emitters and reflectors diffuse, and it's called the diffuse view factor. The view factor based on the assumption that the surface are diffuse emitters but specular reflector is called the specular view factor. The view factor has proven to be very useful in radiation analysis because It is allow us to express the fraction of radiation leaving the surface that strike another surface in terms of orientation of these two surfaces relative to each other. The underlying assumption in this process is that the radiation of a surface received from a source is directly proportional to the angle the surface subtends from view from the source. This would be case only if the radiation coming off the source is uniform in all directions throughout its surface and the medium between surface does not absorb, emit, scatter radiation. The case when the surface are isothermal and diffuse emitters and reflectors, and the surface are separated by non-participating medium such as vacuum of air. So the view factor of hundreds of common geometries are evaluated and the results are given in analytical, graphical and tabular form. So next is the geometry of finite size in 3D and the relation. So the different geometry, there are different type of relation. So here's the eight type of geometry. So you can see that geometry and the relation. So the radiation analysis of enclosure consisting of n surface require the evaluation of n square view factor. So next is about the summation rule. So you can see that from the figure, the radiation leaving any surface I of an enclosure must be intercepted completely by the surface of the enclosure. The sum of the view factor from surface I to each one of the surface must be unity. So as you can see that from the equation, if I to j is equal to 1, either it's 1 to 1, 1 to 2, 1 to 3, so the summation is equal to 1. The remaining view factor can be determined from the equation that are obtained by applying the reciprocity and the summation rule. Next is about the superstation rule. So the figure shows that the surface to a composite surface is equal to the sum of view factor from the surface to the part of the composite surface. The view factor from a surface I to a surface J is equal to the sum of the view factor from the surface I to the part of surface J. So the equation will be like F1 to 2 plus F1 to 3. So there's the first, and the next is FAF plus AF over A plus A. So next about the symmetry rule. So you can see the figure. As you can see at the equation, you can see that F1 to 2 is equal to F1 to 3. It is because the possessed symmetry about the third surface will be identical view factor from the surface, and any of the from 1 to 2 to 1 to 3 is the same symmetry and same identical view factor from the surface. So next is about the superposition rule. So the view factor between infinite long surface, the cross string method. So the channel and duct that are very long in one direction relative to the other's direction can be considered to be two-dimensional. These geometries can be modeled as being infinitely long, and the view factor between the surface can be determined by the simple cross string method from the figure. As you can see that, so there is a line 1 until line 6. So determination of the view factor F1 to 2 by the application of the cross string method. So after presenting about the view factor, so the next one is exchange between surface and also radiation network. So at first I will explain about the diffuse gray surface. So most enclosure encountered in practice involve non-black surface which allow multiple reflection to occur. Radiation analysis of such enclosure become very complicated unless some simplifying assumptions are made. It is common to assume the surface of an enclosure to be opaque, diffuse and gray. Also, each surface of the enclosure is isothermal and both the incoming and outgoing radiation are uniform over each surface. So the next one is about the radiosity. So from the figure, I can explain that the incident radiation. So from the incident radiation G, it will reflect into two. There is reflected radiation and emitted radiation. So that one is called radiosity, also pronounced as J. J is mean by the total radiation energy leaving a surface per unit time and per unit area. So the radiosity of a black body is equal to its emissive power since radiation coming from black body is due to emission only. So next is net radiation heat transfer to or from a surface. So during the radiation interaction, a surface loses energy by emitting radiation and gains energy by absorbing radiation. So which means that the radiation in the surface lost energy by emitting and also it will gains energy radiation emitted by other surface. So a surface experience net gain or a net loss energy depending on which quantity is larger. So from the figure, the surface resistance to radiation for a black body is 0 since equal to 1 and J equal to E. So the some surface are modeled are being adiabatic since they are backside are well insulated and the net heat transfer through them is 0. So after the radiation to and from a surface, next one is between any two surface. So as you can see from the figure, so there are surface I and surface J. So between surface I and surface J, there are net radiation. So the considered there are two diffuse, there is gray and opaque surface maintained at a uniform temperature as shown in the figure, and the J representing the rate of radiation leaving surface per unit surface area, and the view factor F1 represent the fraction of radiation leaving surface I that strike surface J. The net radiation heat transfer from a surface iceberg can be expressed as an equation. So it will be minus. So this one is a different ontology. So in an end surface enclosure, the conservation of energy principle you require the net heat transfer from surface I be equal to the sum of the net transfer. So it means that from the surface I will be from Ji to J1, J2, Jn and Jn. So it will be uh, equal to the sum of net transfer. So the net radiation flow from a surface through its surface resistance is equal to the sum as I said just now, and radiation flows from the surface to all other surface through the corresponding space resistance. So from the figure, as you can see that, so from the Q, from the J, it will be equal to J1, J2, Jn minus 1 or Jn. So it will be in the equation. So next is two surface enclosure. So the net of radiation heat transfer from surface 1 and surface 2 must be equal. The radiation network of two surface enclosure consists of two surface resistance and one space resistance. In an electrical network, it also can be solved in the electrical network. So the electrical current flow through this resistance connected in series would be determined by dividing the potential difference between point A to point B by total resistance between the same point. As you can see from the figure, from the E1 and the E2 to E2, there will be the electrical network that is resistant. So Q1, Q12, and Q2. So the equation will be R1 and R122 and R2. The schematic of two surface enclosure and the region network associated with it, yes. So after two surface, it will be three surface. So the schematic of a three surface. So there is 1, 2, and 3. So from the surface, from the figure, you can see that from Q1, Q2, it will be Q3. It will be connected and the resistor in the middle and the equation. So there is a draw of surface resistance with each of the three surface and connect them with space resistance. Yep. So the radiation shield and the radiation effect. So as you can see, the radiation heat transfer between two surfaces can be reduced greatly by inserting a thin sheet of material between two surfaces, just like this, between two surfaces. And such a highly reflective thin plate or shield are called radiation shield. A multi-layer radiation shield constructed of about 20 sheets per cm thickness separated by aggregated space are commonly used. So radiation shield also used in temperature measurement of fluid to reduce the area of caused by a radiation effect when the temperature sensor is exposed to surface that are much hotter or colder than the fluid itself. So the role of the radiation shield is to reduce the rate of radiation heat transfer by placing additional resistance in the path of the radiation heat flow. So the lower the emissivity of the shield, the higher of the resistance. So from the figure below, shows that there are network shield, a radiant shield between two surfaces. So it will be equation that is the EB1 to EB2. There will be J1 and J2. There is like shield. So consider the radiation and the radiant heat exchange between two non-black surface and electrical network representing space and surface resistance to radiation R from the figure below. So the radiation shield between two parallel plates, the radiation and the radiation network associated with it. So as you can see that the shield between the two surface and the equation, yep. So next and lastly, the radiation shield reduce the radiation heat transfer by effectively increasing the surface resistance without actually removing of heat from overall system. So that's all from me. Thank you.
Assalamualaikum warahmatullahi taala wabarakatuh and salam sejahtera. My name is Nur Muhammad bin Muhammad Toni from section 11 So today I'm going to show you about the two subtopics of radiation heat transfer, which is subtopic 7.4 spectral and directional dependence and subtopic 7.5 total hemispherical property. So for the subtopic 7.4 spectral and directional dependence, sometimes it is necessary to consider the variation of radiation with wavelength as well as direction, and to express quantities at a certain wavelength. Such quantities are referred to as spectral quantities to draw attention to wavelength dependence. The modifier spectral is used to indicate at a given wavelength. The spectral intensity for emitted radiation can be defined as the rate at which radiation is emitted at the wavelength in the direction per unit area normal to this direction per unit solid angle about this direction. So the equation shows the rate at which radiation energy is emitted at the wavelength in the direction per unit area normal to this direction per unit solid angle about this direction. The most elemental emissivity of a surface at a given temperature is the spectral directional emissivity, which is defined as the ratio of the intensity of radiation emitted by the surface at a specified wavelength in a specified direction to the intensity of radiation emitted by a black body at the same temperature at the same wavelength. You can see the equation as followed, where the subscripts lambda and theta are used to designate spectral and directional quantities respectively. The total directional emissivity is defined in a like manner by using total intensities as the equation shows. So for the next subtopic, which is 7.5, total hemispherical property, the integral of the rate of radiation energy emitted at a specified wavelength per unit surface area over the entire hemisphere is spectral emissive power. The spectral hemispherical emissivity can be expressed as the equation below. So the equation shows a specified wavelength per unit surface area over the entire hemisphere is the spectral emissive power. Note that the emissivity of a surface at a given wavelength can be different at different temperatures, since the spectral distribution of emitted radiation changes with temperature. The total hemispherical emissivity is defined in terms of the radiation energy emitted over all wavelengths in all directions, as the equation below shows that the radiation energy emitted over all wavelengths in all directions. Therefore, the total hemispherical emissivity of a surface at a given temperature represents the ratio of the total radiation energy emitted by the surface to the radiation emitted by a black body of the same surface area at the same temperature. So that's all from me. Thank you for listening and have a good day.